So Dr. Subhajit Pal grew up in a small village in India. He earned his undergraduate and master's degrees in chemistry, followed by a PhD in Switzerland, where he worked on designing biomimetic polymers that can mimic biological functions. He is currently a postdoctoral researcher in the bioengineering department at UC Berkeley, developing next-generation biomaterials for healthcare applications, including medical adhesives for tissue repair and regeneration. Outside the lab, he enjoys gardening and spending time in nature, which continues to inspire his work. Let's welcome Subhajit.
Thanks for the introduction and organizing these sessions monthly. This is amazing. Thanks to all the audience for being here, either in person or virtually, and showing interest to our research work. So, Anu told us so far how to avoid defects in the babies, and I will try to give you a little overview of if a surgeon or doctor figure out a problem inside the baby, how my research can help addressing those. So it goes together really nicely. So today I will talk about the sticky science, much more focusing on the healthcare application. So I'll try to cover what is the key challenge in this field, what is the current state of the field, and where the field is going. Please feel free to ask any question if you have throughout the presentation or if I'm not being clear. So I'm here just to answer any curiosity or question you have. So let's review some of the slides I prepared for this up. So this is a very familiar picture to most of us, right? There are wide varieties of glue, and much more scientifically, they are referred as adhesives, including epoxy, superglue, glue stick, exist in our daily life in household use, from gluing a envelope to fixing the broken cup. So whenever it's come to fixing a torn page in our favorite notebook or fixing the handle of our favorite mop, we just reach out to either Scotch tape or superglue. That's easy peasy, right? No problem. Now let's see what doctor or surgeon do when they found a trauma injuries or surgical injuries in the human body. Ooh, painful, right? So their first go-to is either stitches or staple. Unfortunately, these are still considered the best approach to address surgical and trauma wounds in the human body. If we recall our previous picture, we can all imagine there must be a better way. And there is. We can all imagine there is a gentle, fast way to address those injuries simply by applying one of those glue. So it can address those injuries without producing any secondary damage that happen during sutures or staple, which are of course painful, increase the inflammation, and reduce the healing rate. So think of something like a bandit. You just open the box, applied it either inside or outside body, done. As simple as that. The question is, why still not the case? It is not because we don't have such adhesive in the market. There are plenty of those adhesive or sealant currently exist in the market that can be used in the human body. However, they still found limited application. Now let me ask you why. I'll give you a clue. Have you ever tried to put a band-aid on a wet skin or tried to fix a toy underwater? Anyone? We don't try because we know it's not going to work, right? It's the same reason our body is simply too wet to apply any adhesive. It simply doesn't work. So when we try to apply a glue on a surface, it may appear smooth. However, if you look in microscopic scale, the one of those microscope picture we just showed, you will see there is a lot of microscopic defect. And when we apply the glue, it flow through this microscopic crack and form independent bond and provide us this robust adhesion. However, when water comes to the scenario, it just leave a thin layer of water on those microscopic defects. And now this water acts as a barrier for the glue, it cannot reach to the surface of interest. So it cannot provide the robust bonding. So in addition to this weight problem, there are other long list of criteria the medical adhesive has to fulfill. That include it has to be strong enough to hold the tissue together under continuous movement. Imagine fixing a toy and someone is just moving it all the time. It's just way too messy, right? It's get all over. In addition, it has to be biocompatible. It should not release any toxin during its application period. Moreover, it also has to be biodegradable. In another way, it has to degrade when body heals. Because if there is a foreign material present during natural body's healing process, it will interfere with the natural healing, and that will create all sort of other problems. Now, the researchers, that include scientists and engineers, try to put these criteria in a synthetic adhesive. However, main limitations still remain. The most of these synthetic adhesives show poor underwater adhesion property. The researcher has this problem. Like we go to the lab and every day we think we can solve all the problems. We try really all the time. And at some point we come to this understanding, oh, we can't solve it. And then we go out and look into nature because most of the time nature has actually solved those problems. It just we didn't look in the first case. And this is also true when it comes to the adhesive. So there are a lot of creatures which form their house or nest or stick to the rock underwater and create those adhesives. One of those examples is marine mussel. If you walk across a bay, you will see a bunch of these mussels sticking to the stone. And if you try to pull them apart, don't do it if you don't have a fishing license. But if you have, try it. It's not easy. It takes really significant force to pull them apart because they all stick together simply by using this small thread, often referred as biases, and use this small amount of protein glue. And if we zoom into this, you will see this marvelous picture. This is this biases and attached to this rough surface through adhesive protein. Now, we saw it multiple times. I just wanted to share that how this looked like in real life. So I put a small video, and we had a marine mussel in our fish tank, and we see or observe how it does it. So this is a mussel food, is bringing the food out and looking for a surface to attach. So these creatures, they don't have an eye, they sense everything through this food. They're extremely sensitive to the substrate they want to attach to. So this is a plexiglass. It's like the substrate and it's kind of attached. But if you use the silicone, it's not going to attach. It's just going to move around. So here, if you notice, there is a white spot being developed. So that's where it's going to inject the adhesive protein. So now this liquid protein will be injected in that spot. And the cool thing is, as soon as it's come out, it's cured immediately in contact with the water. So you see that it's now slowly injecting the glue, and it takes about a few seconds, and it just leaves the adhesive on the surface and retract it. And if you notice here, you will make out this adhesive, a very thin layer of adhesive. Now it's done its job, and there you go. It's leave this small thread attached to the surface. It's really, really small. They produce a bunch of those all together to stick. Now, of course, after seeing this, scientists got curious, as we always think that we are the most creative one, but actually we are not. We just mimic from nature. So all the researchers studied this protein, that include our group and other group across the globe, try to figuring out that what is the secret sauce behind this strong adhesion. And what we observed, the mussel food protein content an unusual amino acid in very high extent, which is referred to as dopa. So it's an post-translationally modified amino acid. After tyrosine, it gets oxidized to dopa, and thus That's how it's formed this strong adhesion. Now, once we understand how it does the job, of course, our group and others try to develop muscle-inspired adhesive for healthcare application, non-medical application. Here, I just put one example that we can all correlate to. Sticky note. So if you ever try to put a sticky note on the wet surface, you'll realize it just doesn't work, right? Just fall off. Let's see what happens if we try to make a sticky note with muscle-inspired adhesive. So here we put this small dopamine molecule in those sticky notes, and let's see. So this is the commercial one. We put it underwater in a stainless steel. It can't hold it. What happened here? It's exactly the same paper. We just change the adhesive. There we go. It can hold the adhesive for significantly longer time without any issue. Now, as cool it looks like, we are still far from mimicking the exact condition that muscle do it so nicely. All the design muscle-inspired adhesives still need a lot of modifying because currently the muscle-inspired adhesive require complex storage condition and complex application, still far from being used in the real-life clinical setting. So here I will switch the gear a bit and I will talk about the latest adhesive we developed right now at the UC Berkeley, and we are trying to explore what's the extent of the addition we can get there. So in this case, we again exploit one of the natural molecules. So that's termed as alpha-lipoic acid. It's actually an FDA-approved over-the-counter drug. You can go to any pharmacy here and buy it in kilogram scale. And people actually take it as a nutritional supplement. Especially if you know a friend try to growing the muscle, they take it almost every day. In some countries, it's also used to treat diabetic neuropathy. So what we did here, we take this alpha-lipoic acid, dissolve it in hand sanitizer spray, alcohol spray, and we add a derivative of this molecule. I'm not going to get into the details of that, but simply you can take this molecule, dissolve in alcohol, and add it in water. You will see as soon as it's come in contact with water, it's cured almost instantly like muscle protein. Here is forming this thin adhesive layer. So in this technology, we have used water as a curing agent rather than a problem. And this adhesive that we make on the air-water interface, again, you can pick it up and you can see it forms a nice stretchy thread like those muscle protein. It's very sticky. It's a picture we took it at some point, and it can also take multiple forms. Like it can be applied as a liquid, like super glue. You can also make it as a double-sided tape, like a band. Now, the next step, we of course investigated its efficacy to be applied inside the body. So we secured a few organs from the butcher shop and tested this adhesive in the lab. So that means the next slide contains some picture or videos of the organ with a lot of blood and things. So if you are sensitive, you may want to skip the next slide. So to test its efficacy, we obtain a pig stomach, fill it with a color liquid just for visibility, and make incision and just apply our adhesive. As simple, no cleaning, no sutures, no complex procedure. And then we just simply spray with water just to make sure it's cured. And just within 60 seconds is provide leakage-free sealing. And of course, we did a lot of rigorous movement just to show that the adhesive remains on the stomach and doesn't delaminate. We also studied or did a similar experiment with a lung. So again, we took the lung, make incision, then apply the adhesive, and we can see it can successfully stop air leakage and also stretch with the tissue and maintain on the lung surface even after repeated inflation. Now, I want to walk you through when we make an adhesive, what kind of tests we do in the lab just to make sure that it can be used for the biomedical application. There are several steps, and I will break it down for you. So the first thing we test, of course, how strong is the adhesive? That means how much force it needs to pull it apart. we use a lab share test, or this is what is referred to study that. It's a very simple experiment, actually, we all do all the time. So we take a small amount of glue, put it between two surfaces, which can be tissue or piece of plastic, put it together, and then put in the instrument that try to detach it and measure the forces required for it. And this is kind of the real life data look like. So this one is the one we developed at UC Berkeley, and this one, what you can buy from Super. Now the next come, how stretchy is the material? Does it break when the tissue move? Because as we know, all the human organs are very stretchy and it's move all the time because we are not the people that stay all the time in the bed, right? And so we have to test that. And we do that through uniaxial tensile test. So for that, we just cure the glue and then cut into dog bone shape. And when I refer to dog bone, it's the same dog bone that's coming to your body. So we take the dog bone, put it in the machine, and again stretch it until it breaks. And the adhesive we develop, for example, here, we can stretch more than 1,000%. That means it's highly flexible and it can expand with the skin or any other organ, for example, lung. The next is how long this adhesive survive in the body. If it's degraded within a minute or dissolved, then it's not useful, right? We want it to match the body's natural healing process. So we have to study that very carefully, like whether it lasts for a minute, days, or weeks. And again, it's a very simple study. We put the adhesive in the physiological media, whatever is the media relevant to, and we see how much mass loss happens over time, or how long it takes to complete dissolution. As simple as that. And the last list comes that is the adhesive safe to use in the human body or not? And that comes with a two-step process. So first, we grow some cell in the petri dish, so no ethical concern. Then we apply our material to the cell and count how many cells survive when the adhesive was used. So if it passed, there is an FDA approved standard. It's called ISO 1099. So more than 70% cell has to survive to consider it is bioengineering. So if it's passed that test, then we took the material and test it in small animal model to ensure it can be actually used for human application. And of course, this test is done with a veterinary supervision and a lot of ethical approval. So there are several clinical applications you can think of with the glue, right? Everything can be fixed with the glue instead of sutures. So we study a lot of applications, but one of the key applications that we are interested in fetal membrane repair. So there are a growing number of fetal intervention is being performed that include diagnostic procedure, as Anu was referring to, any genetic defect, or some sort of reparative surgery, for example, spinal bifida repair. So it's an incomplete closure of the spinal. So surgeon wanna go in before the baby is born to repair those problems so it can heal before the baby born. So generally, these fetal surgery are performed in the second and third trimester. To do the fetal surgery, is required breaching this fetal membrane. Imagine it's a balloon and the baby is being developed there, so you need to break the balloon to go inside, right? And the problem is the fetal membrane does not heal like any other tissue. So when the fetal surgery is performed or fetal membrane is breached, this increase the chances of premature rupture of membrane. It's actually in almost 30% cases the premature rupture happen, whereas in the healthy pregnancies it's limited to less than 3%. And unfortunately, the 14% fetus survive when they are born before 22 weeks. Therefore, fetal surgery increased morbidity and mortality. Moreover, there is a huge economical burden with the preterm. So our goal is to develop a fetal membrane sealant or adhesive, which can be applied during fetal surgery, so it can seal the fetal membrane after surgery, and also increase the stability of the membrane to increase the gestational period and reduce the morbidity, mortality, and financial burden. So towards this goal, we use our alpha-lipoic acid platform and develop a fetal membrane adhesive and tested its efficacy in small animal model, especially in the time pregnant mouse. So here, on the time pregnant mouse, we perform fetal surgery at gestational day 15 without any adhesive. So we make a small incision in the fetal membrane or with an adhesive. And at the end of the gestational period, we did the sampling and we saw 0% survival when the surgeries was performed in absence of any adhesive, whereas 100% fetal survival was observed when the surgery was performed with adhesive. So this established excellent efficacy and usability of this adhesive. Currently, we are planning a large animal trial in the near future. We will see how that goes. Keep in touch so you will know. Just see UC Berkeley website. I'm sure they will announce. Okay, before I stop, I just want to just make a small comment about where the field is going. As you all know, that we are going towards much more robotic surgeries. So researchers are trying to develop adhesive which can be integrated with those robotic surgery. Moreover, researchers are now actively looking into developing adhesive which can not only repair but regenerate native tissue-like function. For example, I had an accident and I broke my fingers and I had a lot of sutures and now it's fixed. It doesn't move, doesn't have native tissue-like function. But imagine you apply material without the sutures and you regain the whole function. In addition, with the increasing problem with the global plastic pollution, of course, the sustainability become one of the major criteria that we need to fulfill, and everybody is looking into that. And with this, I will stop by thanking my research group, all my students, of course, the popping the science bubble, all of you, Berkeley Public Library, to giving us this amazing platform, and all of you for your kind attention. I'll be happy to answer any questions. Thanks.
I have a question about, so like, for example, with the examples that you showed, the ex vivo examples, is the glue kind of applied, or if there's like really deep lacerations, is the glue kind of just on the surface so that the two kind of lacerated points are still connected, or is it seeping kind of into the laceration to force the closure, if that makes sense?
Yes, absolutely. So it depends on the glue you use. So our target is of course not to apply the glue in the laceration site, just to on the top. So the laceration site stay as close as possible so they can heal with the natural healing process. However, if you have a degradable glue, it doesn't matter because it's gonna degrade over time and it's gonna heal. But if you use a glue, for an example, the medical super glue that you cannot buy, you have to have a medical license. Those, if it get into those laceration site, that's a big problem because those doesn't degrade and this will interfere with the healing process. That's one of the reasons that why we can't buy the medical super glue. This can be only applied by practitioners. Yeah.
So the internal stuff you're talking about, organs, fetal stuff, is absolutely needed. So this question might be a little irrelevant, but is scarring part of the conversation or not?
It is. It is. So the scarring is a big problem, right? In a lot of functioning tissues. For example, when I was giving my example, my hand that I can't move because of significant scarring. So that's where the regenerative medicine kicks in. So we want to have an adhesive that's not only just repair, it's repaired without any scar formation. So we can gain the full function. So of course, it's a one step at a time. So now we're trying to solve the adhesive problem, and in the future, of course, the scarring is very important. Sure.
The adhesive pad that you showed, is that just pure glue that basically you have regular glue on top and then the pad is just pure glue so it will also dissolve alongside, or is it made of something else?
So it's made of the same glue. Think of it as a double-sided tape. So it's already an adhesive sticky. So you just take the thin film and apply it on the top, and that's it. It's already cured. We apply the water just to make sure it's cured further. So we stop the curing at the intermediate state, so it still stays sticky. And as soon as stick, we just spray extra water and done. Because you don't want to have a double-sided tape inside your body because it's going to stick to other organs. So we just need a one side that stick to the targeted tissue, another side not stick.
Probably follow-up question.
Sure.
If by mistake or had incorrect location, it's a suture, you can just cut it out. What happens in this case? Can you degrade it quicker?
So yeah, there are ways to degrade it quicker. We are actually we work on a system like that, but it's not really that simple. If you ask me about whether this is in real life, not really. This is still in the stage of science development, but it is possible. But what you are referring to, it is to some extent problem. With the adhesive, you have to make sure you put in the right place. However, if you have a degradable adhesive, you really don't care because it will degrade anyway. You can just apply one more bandit on top of another. Yeah.
When you showed the graph about like dissolving in some physiological media, is that about 20 days or how soon is that dissolving?
Yes, so this example, we showed it in 20 days, but we can tune. So depending on the organ, so every organ heal at a different rate, right? For example, bone takes over 6 months, whereas the lung like heal within 10 days. So we want to have a biomaterial or adhesive that degrade within 10 days for the lung, but for the bone, it can last long. So these are just designing differences that we can tune the degradation.
There is possibility to like, so if those are you want that sticky thing to be there until
Right,
after delivery. I don't, yeah.
right, yeah.
It is possible.
It is possible, yes. It degrades, but you can tune the degradation rate right really slowly, so it takes like 6 months to degrade. And one thing to note that the fetal survival rate increased exponentially after 22 weeks. So all you need is actually 3-4 weeks of extension in the gestation period. So it's increased from 14% to 95% just within a couple of weeks.
Great talk, I really liked your video. One question I have is like for the lab shear test, or like just in general, does the adhesive depend on like the substrate that you're adding, like different organs or skin versus like a different kind of organ?
It does. So different tissue have different morphology, that microscopic structure I was talking about. If you have a really, really smooth surface, the adhesive have hard time to anchor to. However, if you have very rough surface, it's gonna respond better. So that's why we actually need to study almost any tissue we are interested in. So we study at least 3-4 different types of tissue to make sure we have a good adhesive or a versatile adhesive that can work across different surfaces in biological systems.
And when you do like the lab shear test, like all I'm envisioning is like you have to have the adhesive touching skin and then but what if like the skin is what rips before like the shear actually occurs?
It's actually happened more often than you think. So there is one of the visualizing undergrad that works with me, Joaquin. He does those tests almost every day. And so what we do actually, we take a piece of tissue and take a piece of plastic and glue the tissue like with the hardware store super glue and put the tissue with the plastic. And we roughen the surface of the plastic so the glue stick better. And then we put our glue on the surface that's never been exposed to the adhesive. And we bring another joint and put it together. So tissue, our glue, and tissue. And then the rest of the tissue is attached to the plastic because those tissues are very flexible. We can do the lab shape. It's very often the tissue fall off from the plastic because the hardware store glue is not strong enough. So this is a problem that we encounter all the time. So we do like 8 times or 6 times the repetition, and whatever breaks, we just exclude those numbers. Although those will be better number because we can imagine they're stronger, but we have to exclude those numbers to reportedly reproduce.
One question is,
Yeah.
can you use this glue, because it seems like a surface glue instead of going into the lacerations, can you use this glue in tissues where you've made it thick, like thick tissues? Because then you're seeing one side, but the other side is still kind of stretching.
Right.
So do you have a solution for those scenarios?
So it depends on the how much mechanical force you need. So if you need really a lot of mechanical force, that if the tissue is a load-bearing tissue, or I don't know, then of course you probably need to glue them all the way to get enough mechanical strength so that it can hold together. However, some of these adhesives are very strong and you can just apply on the top surface. And yeah, I see what you're saying. So when it's stretched, it's just open up the lacerals inside. It does happen, but as long as you try to keep together, they will heal in through natural healing process. So we really don't have to glue them all the way across the width for the tissue. Just we need to keep them together.
You mentioned you garden. How does gardening inspire your work in the lab?
That's what I was telling, right? I go to garden, and most of my plants is eaten by slug or snail. So they leave a thin layer of those slimy thing on the top of the leaves, and I know, okay, this is something that survived long in the environment. Maybe we can make something like that. The same is true for the mussel and all this stuff. So we go in the nature, or I go in the nature, I just dig the soil, and something always there that inspire your next thought. I guess that's how it is.
People are speaking over that. Okay, so I just have one last slide for anyone who's interested in joining our listserv. So this is our QR code. If you'd like to scan and join our listserv, we send one email every month, maybe two. And our next seminar will be on June 16th, same location, 5:30, Tuesday. And we have two talks again. And the first one will be in molecular cell biology on Asian DNA from our human ancestors, genetic secrets of the Neanderthals. And the second one will be in physics on how plasmonic nanoparticles use light to break chemical bonds. So if you're interested in learn more about biology and physics, please get the QR code and Alice will see you next month. And thank you again to our speakers for the very interesting talks, and thank you all for attending. And yeah, thanks.
Okay.